13.8 Part 2. I'd like to continue our discussion of the second derivative test by looking at this example. What I'd like you to do is turn off the video, find and classify the critical points of this function, then turn the video back on. Do that now, please. I find my partials, set them equal to 0. That gives me my critical point. Now I work on the discriminant by finding the second partials and by finding the discriminant and by evaluating it. The second derivative test in this case is inconclusive and misses the absolute min at 0, 0. Do the same thing. Find and classify these the critical points of this function. We're going to find the partials, set them equal to 0, find the second partials, find the discriminant, evaluate the discriminant, and again I get an inconclusive test, and in this case I have a saddle point. I'd like to switch our topic now to a discussion about absolute max and absolute min. If your function is continuous and your region is closed and bounded, there will be an absolute max and min. To find the absolute max and min, we evaluate f at the critical points and compare those values to the max or min of f on the boundary. With open or unbounded sets, there may or may not be an absolute max or min, so you wouldn't use this procedure. This is for closed, bounded sets and continuous functions. And we're going to go through these 4 steps. Notice that we're not using the second derivative test. There's no need to classify your critical points. Just find them and evaluate them. So I'd like you to do that now. Find the critical points of the function. Partials, and set them equal to 0, and here's your point. After you find the point, you evaluate the function at the point, and I get 3. Step 3, find the max or min of f on the boundary. Look at the boundary of R. What is it? The boundary of R is a circle of radius 2 centered at the origin and can be described by parametric equations. We take these parametric equations, substitute them into f of x, y. By doing this, we can describe f in terms of one variable. The function looks rather ugly, so we need to clean it up. This is what I get for the cleanup. Technically speaking, I should not call this function f. However, as long as we stay on the boundary, each point x, y can be written in terms of theta. And so f on the boundary can be viewed as a function of one variable theta, reducing our problem to a single variable problem. We're going to find the max and min on a closed interval with a function of one variable. These are the 2 critical points that I get. We're going to evaluate the function at the critical points and at the end points. I like to make a table for such things. And this is what I get for the evaluation at the endpoints and the critical points. The max of f on the boundary occurs here. I take theta equals 3 pi over 4 and I translate that using the parametric equations, translate that in terms of x and y. Do that for the min as well. This is everything we've done. We have evaluated the function at its critical points, and we have found the max or min of f on the boundary. Looking at these three evaluations, I choose my largest and my smallest. So I had a continuous function on a closed bounded set, and so it has an absolute max and an absolute min. The max occurs on the boundary, the min occurs on the interior. The third point that we found gives a min on the boundary, but it's not the absolute min. And here is the same graph, but in terms of level curves.